Okay.
Hi, Matthew.
All right, Matthew, this one's for you.
Oh, yeah, Matthew.
And so I don't have to repeat myself very much. Okay, so let's look at these problems together. Shelby, can you read that first problem to us?
Write an equation of the form y equals a sine bx or y equals a cosine bx to describe the graph below.
All right, so they want us to write a function, and we're looking at a graph. That sounds opposite, doesn't it? Like pretty much this whole time, they've given us the function, and we need to write the, we need to graph it. Now they're actually giving us the graph, and we're going to have to build the function. We've got some choices here. We can call it a sine, or we can call it a cosine. What do y'all like?
Sine.
You like a sine graph? Okay.
Could it be a negative?
Yeah, negative cosine.
Could it be a cosine graph? Yeah. It could be either one of them. Okay. But we do need to be aware here. Now, a sine graph normally, starts off like that. And a cosine graph normally starts off up here, which you know. Now, if we make this a sine graph, what are we going to have to do? We're going to have to shift it back and forth, okay? And now, shifting it, left or right, would be something like sine of, x plus or minus some phi value. Does that make sense? Okay? Now, in the instructions, they tell us it needs to be of the form y equals a sine bx or y equals a cosine bx. So from that instruction right there, phase shifts, not allowed. Okay? Which is actually kind of easier for us because does anybody really like phase shifts? No, nobody really does like phase shifts. So yeah, we're going to start thinking about this in terms of a negative cosine because normally cosine would be up here and everything's flipped. Alright? So we're going to make this in the form y equals a cosine bx. We've already got a couple of ideas. We think there's going to be negative there, which I would agree. What about the a? What's that value going to be? 1.5 or 3 over 2? Yeah, let's put it as 3 over 2. It makes it look really fancy. Cosine. And this is the only mystery part, cosine bx. 4. Why do you say it's 4? How are y'all just coming up with these numbers out of
Because you do 2 pi divided by 1/2, right? Because you do.
The period is at like it ends at a half,
Okay, the period is a half. Okay, I'm going to write that down since y'all said it. Now what?
Well, you do 2 pi, because the normal period is 2 pi over 1/2, which would give you 4 pi.
Okay. Let me see if I can deconstruct what y'all are saying here. Okay. Normally, when I have that b, the formula is the period is 2 pi over b. Now they're putting b there. We used to put omega, right? But are y'all okay with having b rather than omega? Okay. So in this case, we actually we don't know what b is, but we need to know the period. So you could multiply both sides by b. At the same time, divide both sides by the period, and so b is going to be 2 pi divided by the period. Y'all probably doing all sorts of stuff in your head, but this is how I would demonstrate it, how I would teach it. So 2 pi divided by 1/2. Your fraction multiplication, that's going to be 2 pi times the reciprocal. So times 2 over 1. And that's how you get the 4 pi. And that's going to work every single time. Some of y'all are shouting out 4 pi before we even know what the period is. graphs like that. That's great. So there's your answer. Negative 3/2 cosine 4 pi x.
So it's 4 pi x?
Yes, because 4 pi is the multiplier, and x is the x-axis, is the independent variable. Other questions? I'm watching. I wish I had this. I wish I had it back. I'm watching some videos on iTunes U. Do y'all know what iTunes U is? It's pretty cool. They've got sorts of college classes and stuff. You can watch an entire college course on multivariable calculus from MIT, which is actually a pretty good course, by the way. And one of the classes I was watching, whenever he's got a class of 3 lectures hall of 300 plus students. This is at Stanford. And whenever somebody asks a question, he's got this big bag of candy. He just kind of throws it at them. So I was about to say, we'll find some candy, but y'all are so small, I'd run out of candy. We have candy all the time. But anyway, I thought that was pretty cool. The thing is, though, sometimes he throws it up, and he just kind of watches it, and it doesn't go anywhere near the person who actually asked the question. But it's his way of encouraging questions.
Very motivating.
I would think so.
I would answer a lot of
You
questions.
should ask a lot more questions, like bag M&Ms, whatever.
Yes.
Okay, on 12, what do we think? Sine or cosine? Tangent? I like that thinking. Yeah, definitely sine. It's because it's starting here, going up, coming down. What is that? Is that a 6 pi? Okay. So we're gonna look one into the form a sine bx. What do you think a is? I agree with you. 3 is the amplitude. So, okay, so 3 sine, and then our formula is that the period is 2 pi over b. All right, so therefore b is going to be, you can just actually switch and throw those two. 2 pi over the period, so 2 pi over 6 pi.
1/3.
So b is 1 over 3. So this is going to be 1 over 3 x. Or sometimes you could write that as 3 sine of x over 3. That would also be acceptable.
Would you not need the pi in that one?
Well, they cancel out.
This makes a little bit more sense.
Good. Let's do one more, and it'll probably make the most sense. Any other questions, though, before I erase it? Jesus, head up, please. Kimmy, are we rolling on that? Can you check the
Sure. Yeah.
counter rolling on top? Okay. Last one, what do y'all think here? Sine or cosine? I agree with you with sine. We're going up. Let's see if we can just do this all super quick. So y equals a value, 7 over 2. That's 3.5 for the rest of us. Sine, what's the period? Ooh. Okay, I'm gonna actually have to write this down. Period is 4 pi over 3. Remember the formula that we have is that the period is 2 pi over b, so b equals 2 pi divided by, since we're just switching and throwing those two, 4 pi over 3. And then our fraction math is going to kick in. 2 pi times the reciprocal, 3 over 4 pi. The pi's cancel.
That was 3/2.
3 over 2 is our b value. And we're all going to get hundreds on those problems. All right. Why do we have to learn this? When would I use this? Well, that's the one question that students hate the answer to. Right? Oh wait, do we have another problem? Yeah, we got that. Let's get that. Let's turn the page. Well, let me tell you when you're going to use this. You're going to use this in solving word problems, in solving any sort of situation where something is moving back and forth, you know, in a oscillatory motion. That's what we call oscillations. Left and right, up and down, back and forth, even on a slant, diagonal. Okay? So, Kayla, read to us where it says 15 about the weight on the end of a coiled spring.
The weight on the end of a coiled spring is pulled 14 centimeters below its resting position. The weight is released at time t equals 0 seconds and moves upward,
Oscillating.
oscillating in a simple harmonic motion. It completes one cycle in 4 seconds. Note the upward is a positive direction. Give the equation model displacement v as a function of time.
We can actually create an equation that models this motion. You're like, what motion is that? Well, let's go and draw a picture over here. We're probably not going to do all of those, just they get a little redundant. So here's a spring which is hanging from some ceiling, and there it is in its resting position. That's what we call its baseline position. Alright? Well, somebody decided to go and stretch this spring and pull it down like this. How far? 14 centimeters. Okay? What's going to happen when they let it go? Yeah, boing, 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 boing. I go back up and back and forth, right? So what would that graph look like? It's going to go down here, then it's going to go up, then it's going to actually, well, it probably would not go farther than the ceiling. That would be kind of crazy. But it's going to compress that spring, so at this point it's going to look like. Alright? And it's going to compress that spring, all of that energy that was stretched out, it's now pushed there, and it's going to slow it down, but then it's going to push it away back like that, and then it's going to, you know, stretch it all the way down here, and then it's going to go back up here, and then it's going to go back, and it's going to continue on forever and ever, right? Not actually what happens forever and ever. What does happen in reality, real life? It slows down, yeah. And now the question is, why? Why does it slow down? Anybody know? You don't think it's gravity, but gravity's actually working on it the entire time. It's friction, actually. There's actually friction between all these particles, and as it moves up and it moves down, some of the energy, technically all of the energy in a perfect world, when you let it go right here, all of that energy would turn into the scrunching it up, and then all of that energy would turn back into stretching it out, and then all of that energy would go up here. So if you track the energy, that's where you're going to find some of the energy is lost due to friction. In fact, that the particles, when they're rubbing back and forth and stretching out, they start moving just a little bit faster. They generate some heat, and that's where the spring loses its energy. It loses its energy due to heat. If you were to look at this after maybe about 5 seconds, and you were to take a thermal imaging camera at the spring right here, it'd be all cold. But 5 seconds later, when it was maybe just kind of doing like this right here, the spring itself would be warmer. And it would be warmer by just the amount of energy that it lost. So there's a little bit of physics for you. Okay? So in reality, it actually goes, you know, it goes down like this. It follows a curve, an exponential curve, which we'll talk about when we talk about exponential functions. It's called a damped sine wave, but for right now, we're going to pretend like it's a perfect world, and there is no friction, all right? There is no hatred. Dogs and cats love each other, all right? And so it's going to travel in a perfect, what kind of a wave? Sinusoidal, okay? Ignoring this nonsense over here. What does that graph look like since it was pulled down? Does it look like a sine wave or a cosine wave?
Inverse.
It looks like a, yeah, well, I would careful with that word inverse. That actually is a technical term, but you mean inverted. Inverted. Yeah, it looks like that very first problem that we did. Yeah, it looks like some sort of negative cosine, some negative a cosine bx kind of thing. Yeah, absolutely. What do you think that a value would be?
Negative 14.
14. So negative 14 centimeters, so 14 cosine. And now we've got to figure out what this b is. Yeah, it completes one cycle in 4 seconds, which means it goes up and comes back down right here in 4 seconds. This is based on time. So the period, which that's a cycle. In fact, I might even put the letter T there just to kind of get us in physics mode here. Equals 4 seconds. And so now all of that stuff on that first page is really going to help us out because we know that B is equal to 2 pi divided by period. So B is equal to 2 pi over 4, so it looks like pi over 2. So pi over 2 times, I'm not going to put x though because my independent variable is not x anymore, it's time.
Just little lowercase t?
Lowercase t. Uppercase T is period. To make sure there's not any additional information that I told you wrong.
What do we do with D displacement? Or what does that factor in?
Say that one more time.
What do we do, where did displacement come in?
Oh, okay, good question. Give an equation modeling the displacement D. Well, this function is y equals, which means it's y position, okay? Another way that we can think about that, if this is 0, okay? Displacement is a word which means how far has it been displaced, moved from its original position, okay? So what we called this the y-axis, okay? But when it's pulled down right here and it's at negative 14 on the y-axis, okay? It would also be accurate to say that its displacement is negative 14.
Okay.
It's been displaced.
So, okay.
Okay, when it's up here, it's been displaced by 9 centimeters or whatever. So here's the formula. So what we've been calling the y value is also technically, physically, it's the displacement. So thank you. I did not even see that. D as a function of time. Okay. Now, in high school physics and calculus, pre-calculus, I guess that's when we're in pre-calculus, you're kind of at this sort of awkward position, sort of like junior high. I mean, was junior high awkward for anybody? Junior high is awkward for everybody. If it wasn't for you, you count yourself blessed, okay? Where you're, all sorts of stuff going on, you're a little more aware of yourself socially, but then there's things that you're not aware, so it gets kind of weird. Anyway, but the thing is, you are aware of just enough, okay, that you're like, ooh, I can kind of see how you could use that. But there's like so much other stuff that you're like not aware of. So that this is kind of like the beginning, like this is like the springboard, this is like chapter 0 in like some really cool books on, damping of springs and trying to create a shock absorber system, okay? Not just installing shocks in the car, but like designing the shocks, you know what I mean? Or like creating some new sort of suspension for, I don't know, maybe something awesome like a Mars rover or whatever, like you got to have this fundamental background as your knowledge. So anyway, like I said, I would love to take this and be like, all right, now let's change this and let's put gravity in here and let's deal with this aspect of friction, and in reality it's going to go down based on the type of material that the spring is. But that's what college is for. And not all of you are going to go into that sort of engineering, and that's fine. And some of you will, and you'll love it. So let's keep going. Pick one or two more. We've got the buoy floating, the object moving, or a weight on the end of a coiled spring. I vote not weight on the end of a coiled
I've
spring.
already done that.
Yeah.
An object.
An object moves in simple harmonic motion, okay? That's another phrase that we saw up here. Simple harmonic motion means back and forth and side to side, or up and down, okay? With a period of 5 minutes and an amplitude of 14 meters. At time t equals 0 minutes, its displacement d from rest is 14. Well, I'll do this 14 thing again. And initially, it moves in a negative direction. Okay? At first glance, this one seems really close to this problem. Would you agree with that? Okay? We know it's going to be a sine or a cosine. We know that our A value is 14 meters. We'll get to the big question is it sine or cosine? I'll answer that in a second. Let's take care of the easy stuff we know. A is 14. What's the period?
5.
Period is 5 minutes. So what's our B value? B is 2 pi over 5. Now here's the question. Is it sine or cosine? I hear sine, I hear negative sine.
Sine.
Okay, let's think of it. Now this is, at t equals 0, its displacement d from rest is 14 meters. So where's it starting off?
No, 14 meters above.
So it's just cosine.
Yeah, it's
So this-
Okay, so initially, if this is time, t equals 0, it's starting off there at 14.
Cosine.
And it travels in the negative direction, which means
Down.
it's going to start traveling downward like that.
So it's cosine.
So it's cosine. That's how we interpret that one. So displacement D equals 14 cosine 2 pi over 5.
2 pi over 5 t, right?
Yes. And we have just enough time to talk about the buoy. The buoy. I wonder if there's any seagulls. Because then we could say buoy meets gull. Trey, read it to us about the buoy.
A buoy floating in the ocean is bobbing simple harmonic motion with amplitude 5 feet and period 8 seconds. Its displacement d from sea level at time t equals 0 seconds is 0 feet. Initially, it moves upward. Note that upward is the positive direction. Give the equation modeling the displacement d as a function of time t.
Okay. So you've got the ocean level, but has anybody ever been out on the open ocean? How did you like that, Trey?
I mean, I was on a cruise ship, so.
Okay, so they try to really level things out of that. How about you, Josie? Been on the open ocean?
Like where you go in with your car. It was like,
Ferry?
Ferry?
Yeah.
Oh, ferry, okay.
and then, I mean, there's a lot of seagulls. It's not very smooth.
A lot of seagulls. It's not a lot of what?
It's not very smooth.
Not very smooth.
Yeah.
Especially if you get out there in the middle of the ocean where like the middle Atlantic or middle Pacific where they don't always take cruise ships. I mean, the waves, you know, up and down, and you'll have like 10, 20, 30-foot swells. Okay, that means from here to here. I mean, you can imagine. It'd be pretty cool, actually. It'd be a heck of a ride. So anyway, here's our buoy. It's just gonna look like a cone. Alright, and as the waves come, it moves up and down. Alright, and we're told that at time 0, is it high, low, or medium?
Wait, no, it's
Displacement from
Zero.
sea level at t is 0. So it actually starts at sea level. Okay, and initially moves upward. Oh, okay. There you go. So it's sine. And then everything else is just like clockwork. It has an amplitude of 5, that's your A value. Period is 8 seconds, so if T is 8 seconds, our B value is 2 pi over 8,
Which is pi over 4.
pi over 4, and now all of a sudden, just like that, we can write an equation. T equals
5 sine pi over 4 times.
pi over 4
Plus t.
times T, and we're done. The word problems really aren't
You
that
just have
hard.
to make sure you understand.
Yep, piece by piece. Okay? There is no physical homework for this. There is an online homework that you may begin. Some of you may have already started. You will have all class period tomorrow. Let's go ahead, hold on, because you need to know this next big item. All class period tomorrow to work on that online homework, okay? But they're all as soon as you're finished with the memorization quiz.
Yeah.
So remember, memorization quiz tomorrow, it's on those 6 graphs plus the other stuff that's at the top of the page. You'll walk in, takes the quiz, then you'll work online. I will not be here with you tomorrow, so you'll have to video yourselves so I can watch that video. So, all right. Thanks for watching.
Bye, Matthew.